Welcome to Topic D, Ratios of Scale Drawings. This topic is one that has historically given students quite a run for their money. I don't want to rush through it, therefore we will try to extend this topic out a little bit, and I will actually present one of the lessons, lesson 18, in class, and we'll do that together. But first of all, I want to just talk about this idea of scale. And again, it can be a very confusing idea sometimes to kids. But if you just imagine a scale, okay? Now a scale has to balance, and this scale actually is a really handy tool. I mean, it's a great tool when we're talking about algebra. But I'm not exactly going to talk about algebra in this sense. Maybe I am, actually. Now with scale, if you had, let's say, one thing on this side, okay, you could have one exactly the same thing on this side, okay, in terms of its mass or its weight, and it would maintain balance, okay? But if you did not have that one thing to balance on that side, or you don't necessarily want that one thing to balance on that side, you would have to have two evenly weighted or massed objects that equal the same as that one weight or mass on the other side to achieve that balance once again. And if you're trying to keep this balance, in this sense we have 2 over here for every 1 here. And this looks very familiar to you, I'm sure, in terms of ratio. Okay, 2 to 1 right here. And these two things, they balance. Okay, so any kind of ratio that we see, they balance, where there are 2 on this side, there are 1 on this side. Okay, there's achieve a sense of balance, or a sense of ratio. Okay, so when we talk about drawings, scale drawings, we're talking about things such as drawings like for plans for a home, for example. Let me go find one. So this picture here is a perfect example of what we consider a scale drawing. Okay, so a scale drawing is a drawing where every unit that is represented on the drawing, so let's say here we're talking about centimeters, for example, and again, this isn't real. I mean, this is actually a reduced version of a scale drawing of this this home layout. Okay, but anyway, let's just say here is a centimeter. These are in centimeters. So for every 1 centimeter here, that might represent 2 feet, 10 feet on the original house. Okay, probably not 10, but anyway, that could be. Probably not. But anyway, that's this idea of scale. It's getting back to this idea of the balance. Okay, for every like 1 centimeter we had 2 feet. Okay, so it's that balance, that scale drawing. So if you're going to create a drawing like this is an actual reduction. Okay, so this is an actual reduction of this this home. Okay, and the actual home is going to be an enlargement. Okay, an enlargement of this drawing, this plan. Now, an architect, maybe some of you aspire to be an architect one day, but you know, they're often called renderings, or they're called plans. These right here. Okay, so it's more or less a reduction of the original, but the truth is, the original is probably more correctly an enlargement of this architectural rendering, because at this point at this point here, when you have this drawing only, there is no home. Okay, you're going to actually create a home, and this home is really just in your mind. Okay, if this is the original plan, now this home might have been built many times prior, but but this plan right here is actually just a scale drawing of something you would like to see in real life. Okay, this isn't a scale drawing, but it does have something to do with scale. Can you look at that and tell me what it is? And yeah, I'm sure many of you recognized it as an enlarged, probably we say it's an enlarged detail of a piece of corn, of a corn cob, right? Okay, because you can see the not a cob actually. Isn't a cob? Cob is probably when it's all eaten up, huh? Let's call it of an ear of corn. I know this is really not that important, huh? An ear of corn. Okay, because you can see the little kernels here, those little kernels, and you can see the little strand here, the little hairy fibrous piece going across there. But this is actually, in terms of scale, this is an enlargement. Okay, and so in this case, I'm not exactly sure what the scale was, but it's probably something I'm trying to think of maybe like an ear of corn. Maybe they're about this big. The kernels maybe 1, so maybe 2, 3, 4, 5, whatever. It could be maybe a 6-to-1 scale, or we could even say 1-to-6. So for every 1 centimeter kernel, and on this picture here, it actually looks 6 centimeters, 6 centimeters long. But again, this is an enlargement, okay, and very often this idea of enlarging items is something we do through a microscope. So let's go find a microscope image. Now this is majorly cool, I think. Anyway, this is an enlarged image of a. Can you guess? Really neat, but an enlarged image of a thread through the eye of a needle, and this is actually as it is seen through a scanning electron microscope. And some of you in grade 7 class, grade 7 science, are familiar with this kind of microscope, and we've seen other images actually in our class here. In math class, we saw those SEM images of the vegetables, like the broccoli that we were working with the one day. Yeah. So this is an enlargement, or yes, a magnification more so. This is several thousand times bigger than it is in real life. So this could be like 1,000-to-1. I'm not sure exactly. I should have researched that and looked at it, but yeah, I mean, who knows? I mean, to see a needle, the eye of a needle, looking so tremendously huge. But this type of thing gives scientists, doctors, medical personnel, etc., a chance to see things up close, such as viruses and bacteria and insects, for example. We've all seen our creepy magnified image of an ant, for example. But anyway, yeah, so this idea of scale is that kind of idea. When you scale something up, you magnify it, in a sense, through a microscope. Is very similar, because for every 1 unit of measurement, you are scaling it up, another designated unit. Okay, so you can tell what the real thing would actually look like, or have a better idea. Okay. Now, a few of these images that we've looked at here, this corn, for example, and the needle, and thread, and this here of skin. Okay, these magnifications. These are all 3-dimensional. What we will be mainly involved with here in grade 7, we are talking about about producing scale drawings, okay, because that will be what we'll do. We'll look at scale drawings and we'll analyze them and interpret them, but at the end of this entire topic, you will be creating scale drawings of your own, okay, but we're going to deal with 2 dimensions, okay, so two dimensions, and this whole idea of dimensions is really, really important because there are some things that come up rather quickly in this topic that are probably the most problematic aspects of this idea of scale, and it has to do with this idea of dimensions. Now, real quick, let's just talk about this idea of dimensions. Maybe some of you know this already, but basically we have 3 possible dimension possibilities. Did I say possible possibilities? That's really weird. But anyway, we have 1D, or one-dimensional, and that's a straight line. Okay? So we move in one direction when we measure it. Okay? We move in one direction. Okay? So one direction, one dimension. Okay? That's how we measure this line, is in one direction. And all these dimensions, it all has to do with measurement. Okay? Of course, we're talking about math, right? All to do with measurement. All right. Now we have 2D, which is two-dimensional, which is what we're talking about. We're going to talk about here. We'll talk about our scale drawings. And two-dimensional, there are 2 dimensions. Okay. We have, in this case, we can call that length, and then height. Okay, whatever. So we have 2 dimensions, and these 2 dimensions are applied, and maybe some of you know what to do with these already. You might have heard of area. Okay, these 2 dimensions are multiplied to find what the inner part of this this figure here, or this square or rectangle, probably more so, what the measurement of that is. And when we talk about two-dimensional, 2D, we are talking about what we call square units. Okay, square units, and those units could be from centimeters to miles, feet, whatever. So yeah, we're talking in square units, and that's where you get this idea of the square. Okay, so we have 1D, we're measuring in one direction. Okay, and this one direction does not have to be just like this, like one straight line. I mean, we could look at a square and then we could just measure around its outside, or what we call its perimeter. Okay, and perimeter is also a one-dimensional measurement. Okay, we have perimeter as a one-dimensional measurement. We have length, we have height. Okay, in terms of this two-dimensional measurement we took here, we used actually 2 one-dimensional measurements. We used right here, we used length times height, or width times height. These are both one-dimensional, but when we multiplied those, we got square units. Okay, because what we did is we just split this thing up into squares. Okay, and we got a two-dimensional measurement. Okay, now 3 dimensions. Okay, so of course it's not so easy to necessarily. It's impossible to draw on a plane like this, but I can draw a representation of it. Okay, there are some techniques that can, like the technique I just used to create a 3-dimensional cube, and a 3-dimensional shape has 1, 2, and 3 different measurements. Okay, and again, like with a 2-dimensional measurement, we are actually multiplying again. Okay, and then 3D, we measure in cubic units. Okay, and that's all based on this idea of a cube. Okay, because what we're trying to find out is how many cubes of a certain size. Okay, a 1 unit by 1 unit cube. How many of those fit inside of this larger cube? Okay, just like here, we're trying to find out how many 1 unit by 1 unit squares fit inside of this larger larger shape, whether that be a square or a rectangle. Okay, or others. I mean, you can do an area of a hexagon, you could do an area of a circle, area of a triangle, and some of these things you guys may know already, but I just thought I'd clarify this idea of dimensions, and we'll be working in this right now when we're talking about these scale drawings. We'll be working in two dimensions. Okay, so if you look at your first page here of lesson 16, and lesson 16 is titled Relating Scale Drawings to Ratios and Rates. So right now we're just going to relate this idea of scale drawings to what we've learned already about ratios and rates, and we're going to see pretty much right away how this the constant of proportionality unit rate that we've used in the past is going to be similar or almost synonymous with this idea of scale. Okay, so this first little activity here, classwork activity, is intro, is can you guess the image? So if you guys are looking at these pictures here on the first, you can see this one. I'm not sure how many of you do a lot of traveling by means other than car or bike or foot, but that is it actually is a subway map. It's a subway map, and I think it's actually a subway map from some other place in the world. I think I was looking at my enlarged version, and it looked like, I don't know, some different language. But anyway, yeah, and then this one over here, number 2. Boy, if I had blocked it up and maybe just shown you just a small portion of it, I wonder if you could have told me what it was. But I think in this state you can tell that it is indeed a fingerprint. Okay, a fingerprint that is special to this one person who made this fingerprint, because all of our fingers are differently, though similarly designed in a sense. They are different. They are very unique. Okay, and I think this is a whorl or an arch. Anybody know here? Probably an arch. I think it's arch. I think whorl's a little bit different. You can tell by the patterns here. All different patterns. All of our fingerprints. One of our very special identifiers. Okay. Now, if I were to ask you here, and again we'll get to example 1, which is down below, what kind of or what type of scale drawing these are, what might you suggest about this subway map? Would that be an enlargement, or would it be a reduction? I know, it sounds like a stupid question, doesn't it? But if this is the actual size that I gave you, you can see that this subway map would be, of course, be a reduction. And why would you reduce something to such a small size? Well, to fit it, maybe to fit it as an icon onto your web page, okay? Which is something I would do. I don't really intend for people to actually see what it says, because I sure can't. You guys maybe can, because your eyes are so much better than mine, but this might be an icon for someone to click on my on a web page or something. Now, of course, the fingerprint, unless this person is a giant of some sort, this is absolutely an enlargement here. Okay, and again, why would you want to enlarge something like this, a fingerprint? You might want to enlarge it to see detail. You know, to see the detail, to see maybe some of these marks here, these dark marks might be might be evidence of something of some sort. Maybe this person had an accident and burnt their fingers. You know, if people whose fingers are burnt, actually, their tips of their fingers there, they will lose some of that. Lose some of that design there, some of that pattern. Because it'll all be just kind of singed together. But anyway, yeah. So this is an enlargement, which might be needed to uncover some detail by a forensics officer or forensics person. And then the subway map over here is of course is a reduction. Okay, in our example 1 here, for the following problems, A is the actual picture and B is the scale drawing. Okay, B is the scale drawing. Now they're asking you here, is the scale drawing an enlargement or a reduction? Okay, so we look at the scale drawing. That's the scale drawing. That's the scale drawing. So in number 1, of course, you can see that the scale drawing is an enlargement. Okay, it's an enlargement. Okay, again, this is pretty basic. It's an enlargement. And as you can see here, in number 2, the scale drawing is a reduction. And we've talked about reasons why you want to enlarge or reduce something. Lots of people making copies, making brochures of any sort like that. When we as teachers come up with activity sheets to use in class, we often create reductions of certain items so we can fit them on the page. Okay, and here's our key idea. Scale drawing. This is what we are most interested in this lesson. Here is a reduced or enlarged two-dimensional drawing. So it can be reduced or enlarged two-dimensional drawing of an original two-dimensional drawing. Okay, so sometimes you're going to create two-dimensional drawing of a three-dimensional object, possibly. Okay, but in this case, we are talking about scale drawing only. Okay, so let's consider this idea of drawing. All right, so let's look at here example 2. That's pretty easy to see here. Well, actually, it's not easy to see. Let's not talk about example 2. Just want to talk to you about drawing. So this idea here too. Here's a drawing of a ruler. Okay, and here's the reduced drawing of that ruler. So this is a scale drawing. B is a scale drawing of A. It's just been reduced, and the ratio has to stay the same. Now, with A and B on this side, with the portrait over here, again, the way it is scale is that it has a certain ratio, a certain scale, a certain constant of proportionality, which we'll talk about more in a little bit. Okay, this example 2 is very, I don't know, it's kind of strange to throw this at someone at this juncture. But anyway, these let me read this example, see if it makes any sense. So, Derek's family took a day trip to a modern public garden. Derek looked at his map of the park that was a reduction of the map located at the garden entrance. The dots represent the placement of rare plants. The diagram below is the top view as Derek held his map while looking at the posted map. This is so convoluted and weird. Okay, but you can tell. So what happened here is here's Derek's map. Okay, he's got this reduced. You see, it was a reduction, so you know this is Derek's over here. Here's Derek's map he has, and here is the diagram that was located by the garden entrance. Probably a lot larger than that. So again, really silly example, but we'll go through it anyway. And the idea is, of course, I mean, it is a reduction, so you know that it's to scale because they're telling you so. But you can see what's happening here is that Derek's is being held incorrectly. Okay, so if he were to hold this correctly, he would go ahead and go. Well, I guess I wonder if I could do that. I thought I maybe could do that, but I can't actually spin it around. But anyway, I'll just cancel that. I'm not sure if you can see even what I was doing, but what he needs to do is actually go ahead and turn his map around how many degrees? It looks like, because can you see where these are? You can see where R is here. See, R is the same as A. Okay, because the thing is just flipped over. It is to scale, but he needs to flip this over what? So he needs to flip it over 90, 180. He needs to flip it over 180 degrees. And if he did that, it would end up to be this way. So it would end up to be, you'd be looking at it, it would look exactly the same as this one here. Okay, if we went ahead and flipped it over. I don't know why they threw this here at you right now, but anyway, let's go ahead and, I mean, it might be something you'll see, but not right now. Anywho, let's go ahead and take a look at these questions. So if we go ahead and do our flipping, we would see that point A says what are the corresponding points of the scale drawings of the maps. Point A to point R, and I guess the point they want to make here, excuse me, A and R, A right there, is they want you to know that, you know, it's not W and A are not corresponding points because they are not the correct location, okay, because you can see that's not being held the same way. Anywho, but yeah, point V would correspond to W. You can see that right here and here. And again, this is after, and again, because the reason they're in different locations is because we needed to, remember, to rotate this one at 180 degrees, okay, and they would be the same place. And you can see what happened. You can see how A would end up right over here, where that is, and W would end up right here, where that is. Okay, and now point H, maybe you can, if you haven't done it yet, maybe I'll pause a second here, and point H is right here actually. What does point H correspond to? That's right, it corresponds to P over here. Okay, and then finally Y would, there's Y right here, Y would correspond to N over there. Okay, and hopefully that wasn't too confusing, but again, just trying to, maybe it's kind of a heads up. You know, somebody gives you two drawings and tells you one is a scale drawing of the other. Just heads up, and don't just willy-nilly say that you know, A corresponds to W just because they happen to be in the same general location the way you're looking at them. But if you looked at them the proper way, you know, and if you went and spun it around 180 degrees, you would you would be able to hook them up or find their corresponding points this way. Okay, that's really important though if you are, you know, taking a taking a trip through some gardens like Derek's family. Okay, so the idea with exercise 1 here is to create scale drawings of your own modern nesting robots using the grids provided. This is a modern nesting robot. Doesn't look all that modern to me, but you are going to go ahead and do this yourself, and then come on back and we'll see how yours compare to the one that I create, which could be a mess because I'm doing it on this iPad with this pen that doesn't work very well. But anyway, just something to let you know ahead of time, and the only way this actually works as a scale drawing activity is to show you, to point out that all three of these grids here that are created or in front of you here, both have the same unit measurements. So all three, okay? This one here, the original, right here with the robot already drawn on it, this is the one you are going to base your drawings on, because here you're going to be drawing an enlargement of this original robot. Go back here. An enlargement Oh, I'm doing something, hitting something there, enlargement. I'm not going to mess with that. Okay, so you're going to do the enlargement over here, and you're going to do the reduction down here. Okay, but very, very important is that all three of them are 20 units by 25 units. Okay, they're all 20 by 25. This one is the same, except that all of the units now are larger in terms of their size. Okay, thus they will give us an enlargement. These have actually been reduced in size, but they are the same in number, 20 by 25. Okay, so they are all properly scaled. Okay, so why don't you go ahead and do that, and come on back. Phew, boy, that was not as easy. I hope you had an easier time with that than I did. Doing it on this iPad with this stylus is a little bit challenging. But anyway, you can see what I came up with here. And the way I just wanted to show you, I wanted to show you one way to do it is that you could go back and you can look at your original. You can look at your original drawing, and you could find the points, the various points that make up the kind of the vertices, or the the little edges, or not the edges, but the vertices. Yeah, the points that that you find at different corners. Okay, so that's what I did. I went ahead and I plotted those, and I used a blue marker, quote unquote marker, and then I went ahead and used the original drawing to finally draw my lines. Okay, so I came up with what would be a scale drawing. I didn't do the small one, but hopefully you did the same, and you can tell if what you did matches the original by looking at it. It's not always doesn't always look so perfect. And actually, what I'm noticing right now is that mine is not correct. I'm going to change that right in front of you. Admit my mistake. I'm telling you, this is not. I knew something was wrong over here. I drew my little blue dot too close here. Get my blue dot, because that's like 2 units out. 1, 2. Those go there. There. Yes. There we go. I'm glad you guys have patience. You have patience, don't you, for me? There we go. So there. Whatever. Okay. And hopefully you guys are using a ruler. I can't use a ruler here because it just messes everything up when I try to use one. Alright, now I feel a little bit better about this, and hopefully that is right. Anyway, yeah, so that's the idea of scale drawings. Hopefully you had fun with that. I think this can be quite a bit of fun. Let's go ahead and move on to, let's see, that was exercise 1, right? And I'm sorry, just excuse me here. Okay. Okay, I'll be right back. One thing just to make clear on these drawings, or these scale drawings that we did here of this robot. I don't think I actually said this, but I think you probably do understand this though, because we do understand these to be drawn to scale. You know, this one enlarged here, an enlarged version of this, and this one a reduced version of this. We have to make sure the only way to maintain their proportionality, or their constant of proportionality, is to make sure that you are using similar units. So if you counted over here between, right up here on top of the head, they were 4 units long. This from here to here would also need to be 4 units long. Okay, and that would be, you'd maintain that. You see how I messed that up over here? I actually had this as 1 unit wide, but it actually was 2 units wide on the original. Okay, so I just wanted to clarify that, and that's how it will remain proportional throughout. Okay, as we look at example 3 here and do this together, I want you just to note that there is a section right over here called Notes. Okay, and if you would go ahead and just write some of these important points right down there in the Notes section as we go along. Okay, so example 3. Celeste drew an outline of a building for a diagram she was making, and then drew a second one mimicking her original drawing. I'm not sure why you do something like this, but we are. State the coordinates of the vertices and fill in the table. Okay, so let's talk a little bit about this problem. Okay, so now she already drew a scale drawing. She drew an outline of a building for a diagram she was making, and then she drew a second one mimicking her original. So we're looking at a drawing of a drawing. Okay, we talked about this earlier. Okay, but this second one is this is a drawing of this, and we're going to figure out right now if it was indeed a scale drawing. Okay, because that's our task here. Okay. So now the second part I want to talk to you about this too brings up some important vocabulary. So state the coordinates of the vertices. That's the word, vertices, and we talked about that right here. Okay, we talked about the vertices right over here. Remember, I was plotting these points, and these little points are vertices. Okay, it's little vertices, the corners in a sense. Okay. The vertices and fill in the table. So, here's the original drawing over here. Okay. Now the original drawing height would go up to right here. This would be 18 right over here. Okay. And in fact, it would be 6, 7, 8. Actually, if we were going to do this with an XY coordinate, it would be 18. 8 comma 18, where x is 8. Is that 8 or 7? Wait a minute. Looks like 7. Sorry. 7. That is 7. 18. Okay, see there, x is 7 right there, and then y is 18 right there. Okay? So the only thing we're concerned with right now, though, is the original drawing of the height, and that was 18 units. Let's just put u, because u is going to equal units. Okay, we haven't determined whether it's centimeters, inches, whatever. We're just using units. Okay, 18 units there. All right, and next is the original drawing. Now the length. Okay, so the length is this bit right here, okay? And that's from this point, which is where x equals 7, to here where x equals, what do we have there? 10, is that right? 10? No, sorry. No, 10, 11, 12, 13. 13, okay? So you can see right here, this point, this coordinate point is where x equals 13, and in this case, y equals 0, okay? So you can see, so this goes from, and right here, x equals 7 there, and equals 13 there. So in between here is actually 6 units. Now hopefully you can see what I'm talking about, because we're trying to find out the dimensions of this building, this drawing of a building right here. Okay, and so the way we do it is we're looking at the height, which we figured out. I'm going to just cross it, just take this u out. I just don't like. Just want to put 18, okay? And you know it's units. 18, that's easy enough because it goes from 0 up to 18, okay, right here, 18. And I'm drawing the coordinate points here because I think that's really good to do, okay? That's 18. Now the length is going to be right in here, this portion right here, okay? And here we see that it's 7 here, it's 13 here, and the difference between those two is actually what it is in the middle, and that's actually 6 units. Okay, so in the original drawing, the ratio of height to length is 18 to 6, and if we wanted to go ahead and make a even more particular ratio, or probably a real unit ratio, it would be 3 to 1. Okay, so 3 to 1 with height to length. That's just one thing we can do. The second drawing, okay, we have a height of 9. Okay, and again, you can see this is where x equals 9. And, sorry, hold on a second. Not x equal 9. We have x equaling, that's 7 again. Yeah, 7. 7 and 9 right there. Okay, but we have y over here equaling 9. And we could tell that it's 9 units from here to here. That's 9 units in height. Okay, and then the length goes between 7 and 10. Okay, so here's where x is 7, and here's where x is 10. Okay, so the difference between those is 3. Okay, so 3 units. All right, and we can see if we do a ratio here of the second drawing, its ratio of height to length is also 3 to 1. Okay, and we can also see that the height here has been cut in half on the second drawing, and the length has also been cut in half. So you can see that it maintains this kind of this aspect ratio here. Okay. All right, so that's that. Let's just talk a little bit. Let's ask a couple of questions here. I'd like you to just make a few notes after I ask these questions. So let me just ask you here. So is the second image a reduction or enlargement of the first image? Probably a silly thing to say, right? Okay, of course, it is a reduction. How do you know this? Well, the second image, this one here, the second, is smaller than the first, okay? Than the original or whatever. The first, okay? It's smaller. It is a reduction, okay? And so what do you notice about the information on the table? Okay? The pairs of corresponding lengths are all proportional, okay? You can see that there, right? The 18 to 6 is the same as 3 to 1 for the original drawing, and then 3 to 1 again for the second drawing, okay? So it maintains that proportionality. So does a constant of proportionality exist? Well, kind of just answered that question, and that answer would be yes, okay, because there is a constant value to get from each length to its corresponding length. And that value here, as you can see, if we go from 18 to 9, that is 1/2. Because remember, we're doing y, we're doing k. This constant of proportionality equals y over x. In this case, this is y, okay, and here is x. All right, so we have 9 over 18, which is going to be 1/2. Okay, and again, this one here is also 1/2. You go, from the original drawing to the second drawing, you are actually multiplying by 1/2 or dividing by 2. Okay, so you have that constant of proportionality. All right, and again, I just answered this question, but what is that constant of proportionality? Okay, and in this case, it is 1/2. Okay, because you can go from one to the other by dividing by 2. Now also that way, but going this way from height to length, this way is our 3 to 1, okay, and that could also be 1/3 in the sense that every time you see, now looking in terms from original to the second drawing, we're looking at this ratio of 1/2. Now if we're going to go across here and look at our height to our length, it's always going to be 3 height to 1 length, okay, or vice versa, okay, 1 length to 3 height, okay. So you have two different constants here, height to length ratio here, and then from original drawing to second drawing, 1/2, okay. Okay, so I'm going to have you go do exercise 2 by yourself, or with your parent teacher, with a sibling, friend, whatever, and then go ahead and answer those questions. Of course, you're going to start out by filling out a table because you know how helpful tables are. Okay, so go ahead and fill in that table, answer those questions, and I'll be back. If you would, if you need to, go ahead and look back at what we did over here, and try to remember that, okay? All right, I'll see you in a minute. Okay, yeah, so here I have written all the answers, and you can see we got for A and B both no and no. When we went ahead and looked at these two drawings together, just writing down your table, and your table tells the story. Okay, the height of the original 5, length 3, so we would have an aspect ratio or a ratio here, a scale of 5 to 3 in that sense. Well, not a scale necessarily, but just the ratio there, 5 to 3. The second image would have to match that. That ratio would have to match that of the original. It does not. It's 3 to 2 in terms of its height to length ratio. And you can see there is no multiplier that actually gets us up here in both measurements. So from 5 to 15, you can multiply there by 3, but 3 to 10 you couldn't multiply by 3 because 3 times 3 would give you 9. So there is no, well, it's not 3. Okay, so it would have to be the same multiplier. Okay, going up. So no. Answer to A. Does a constant of proportionality exist? No. If so, what is it? It's not. If not, explain. Well, it's not proportional because, just as we had just talked about, there is no consistent ratio or consistent multiplier. Is Luca's enlarged mosaic a scale drawing? No, it's not. Okay, despite the fact that the second one is bigger than the first one, and sure, looks pretty much, quite similar, and it is indeed actually quite similar on a scale basis, but it is not exactly drawn to scale. So therefore it is not a scale drawing and is not proportional and does not have a constant of proportionality. Okay, we'll end this lesson with just a little summary and a couple of points to be made. You can see here on the screen and in your binder. A scale drawing definition is a drawing in which all lengths between points or figures in the drawing are reduced or enlarged proportional to the lengths of the actual picture. This idea of proportional to the lengths of the original or the actual picture, that is the key. A constant of proportionality exists, okay, between corresponding lengths of the two images. There has to be that constant of proportionality that corresponds between the lengths of the two images. Okay, there's got to be a number, a multiplier that gets you from the length of one to the length of the other, and they both must maintain, if you have a two-dimensional figure like the rectangles we were looking at, the ratio of length to width needs to be the same from image to image or drawing to drawing. Okay. Now, reduction, very simply, is the lengths in the scale drawing are smaller than those in the actual object or picture. Okay, so scale drawing are smaller than those. That's a reduction. Enlargement or magnification, we looked at a lot of those. The lengths in the scale drawing are larger than those in the actual object or picture, like the thread going through a needle. It's much larger than an actual needle and thread in our hand. Okay, one-to-one correspondence. Again, this wasn't mentioned at all in the lesson, but we could talk about it now because then it probably makes a lot of sense. Each point in one figure corresponds to one and only one point in the second figure. Okay, the second figure there is a one-to-one correspondence. They are the same exact size. Okay, so if we went back, excuse me, to this one and did, oops, not that. Made something like this and see where does that go. Let's see, 1, 2, there's 3, right? Okay. All right, so those two now would have, this one and this one have a one-to-one correspondence. Okay, they are exactly the same size, they are congruent, and they are identical. Okay. All right, so your problem sets are on their way, but I did want to actually look at the exit ticket again because there is something that is very important in that I want to just give you a tip about. So in your exit ticket, you're going to have, and I don't have an image of the exit ticket, sorry, but in the exit ticket you are going to be given a figure on a graph, okay, and then you're going to have to draw a new picture, okay, and they're going to tell you there's going to be, yeah, they're going to tell you what to do there. But anyway, I just wanted to point out they're going to ask you, a question they're going to ask you is what is the constant of proportionality, and that's going to be one of the questions they're going to ask you. And I just wanted to, just to let you know when you're looking at that, just to remember that that constant of proportionality is this right here, okay? When you're moving from your original to your new drawing. Okay, so you're going from here to here, or here to here. They have to be consistently the same. So when you go from 18 to 9, you are actually multiplying by 1/2. From 6 to 3, you're also multiplying by 1/2. So there was a constant of proportionality, and that constant of proportionality was 1/2. It's not referring to the ratio of each drawing, like like I did over here, the height to the length of both of these was 3 to 1, as you saw over here. But it's not referring to that. It's referring to moving from one drawing to the second. Though, I mean, you know, the ratio of height to length in both of these needs to be the same for them to actually be proportional. Okay, I just wanted to give you a heads up there. Okay, so again, this is lesson 16, the first lesson in scale, and good luck.